Has this ever happened to you?
Has what ever happened to me?
You try to synthesize some of your code, so you input a specification into the program, and then you wait, and wait, and wait, and after a couple of minutes you give up. Or maybe the synthesizer does. Why does that happen? It's very likely that one of two things happened. Either what you asked the synthesizer to do is too hard for the synthesizer, or you made an error in the specification and asked for something inconsistent. And sometimes those two are kind of the same thing. So we're going to start with one of these. What happens when users make mistakes in their specification, and how we can give them a solution, or some solution anyways. And then circle back to our second option, which is what happens when the problem is hard. And then, of course, an evaluation. So let's start with users making mistakes. Let's suppose the user is trying to synthesize a solution to this task, to get the last name from a variable that has the full name. And the program we're looking for is this one. If we're in a programming by example setting, the user is going to give the synthesizer some examples. And just for convenience, I'm going to name the first two E1 and all of them together E2. But wait, some of you may be thinking, there's a typo in one of the examples. Well, good catch. And what would actually happen with this in a regular synthesis scenario is that the synthesizer would think about it a lot and would either time out or come up with a convoluted program that somehow takes the typo into account in what it solves. Now, it's been suggested before that we could simply try to synthesize without each of the examples and see what comes of that in order to solve the problem without the error specification. But one, that's number of examples plus one many attempts to synthesize. And two, if you assume there can be more than one mistaken example, that gets worse. We'd like to do it efficiently. How do we do that? Well, let's put a pin in that and remember what happens when we do a bottom-up enumeration on a grammar that has all the components we need for the target program. When we do a bottom-up enumeration, so we're combining smaller programs into bigger programs, we want to prune our space, and we usually do this with observational equivalence. As we enumerate the programs, we evaluate them on the inputs from our examples, keep track of what values we've seen, and keep one program per set of outputs as the representative. So first we enumerate programs of height 0, the variables and literals in our grammar, and evaluate each one on the two inputs. And for each of those values, we create an equivalence class. Then from the representatives we've already seen, we start to make trees of height 1, like x.length from x, and index of space in x from x and space. We also do some literal arithmetic, and here we see that, for instance, 0 plus 0 is in the equivalence class of 0, but we've already chosen a representative 0, so we're going to just get rid of it and not use it in the next phase of the enumeration. In height and size-based enumerations, we're usually going to pick as our representative the first program we encounter for an equivalence class for technical reasons. So at height 2, we combine programs with height up to 1 and get, for instance, the index of space plus 1, which we need for our target program, and also the index of space minus 1. We also get 1 plus 1 plus 1, which is in the same equivalence class as index of space minus 1. And then when we get to height 3, we get another program in this equivalence class, length of x minus index of space plus 1, which is part of our target program, which is going to get discarded. So let's take a look at what's happening in this equivalence class. We have 3 programs, at least, that are equivalent based on observational equivalence. And observational equivalence tells us that if we want them to no longer be equivalent, we need to add another example. Or in other words, we're going to refine our equivalence relation with another equivalence relation. When we add the additional input, we're always splitting existing equivalence classes. But an important observation is that index of space -1, which was the representative of the unrefined equivalence class, is going to be the representative of the new equivalence class it's in. How does that help us? What we get is the assurance that the program we would have enumerated for the correct subset of the results is also going to be enumerated on all examples, including the error. This means that we can check the results of the evaluation we already do for observational equivalence as we enumerate and see how many of the outputs we can satisfy as we go. And if we find something that partially satisfies the examples, we can hold on to it until something better comes along. This is what we call best effort synthesis. So we had one program with one example satisfied out of 3, and at some point we see our original target program, which satisfies 2 out of 3 examples. So either we find a 3 out of 3, at which point we can stop, or when we time out, we return the best we have, which is our target program. Great. But the best that we have can actually be more than just one program. There are 2 ways that we can have more than one best effort result. First, we can satisfy the same number of outputs that match, but different outputs. But actually, the exact same subset of the examples can be satisfied by more than one program, because the incorrect outputs themselves can vary. So if the number of examples we can satisfy is no longer the way to tell which program is better, what can we do? Enumerate as many programs as we can, at least until we find one that fully satisfies the specification, and rank them, then return some top k out of those to the user. And for that, we need a function to rank by. The fitness function we use for ranking has 4 elements. How many of the examples were satisfied? More is better. How many of the input variables were used? More is also better. Preferring smaller programs, in the inverse to make more be better. And there's one slightly more complex element, the distance from the output of unsatisfied examples. If the output type is structured, like a string or a list, we can do something interesting. We can ask, of the non-matching outputs, which program brings us closest to the target? In our current implementation, we only do this with strings. And to do that, we use Levenshtein distance. Levenshtein distance is a form of edit distance that counts inserts, deletions, and substitutions of a single character. Normalized Levenshtein distance is the portion of the string which needs to be edited, which is what we'll be using for each output that isn't already correct. So for instance, in these 2 programs that only satisfy one example, we compute the normalized distance for each of the incorrect outputs to see how close we are to the result. And what happens if the problem is just hard? This string transformation here wants us to handle 2 cases, one with the substring SSP and one without it. This makes the resulting problem large. Height 3, 0-based, is where we really start to feel the exponential blowup of the enumeration. So the synthesizer might just not make it. But as it turns out, we have 2 useful partial programs. If you think about it, this is also connected to having errors in the specification. There might be a program that has a condition between the correct program and some handling of the error inputs. And if our synthesizer were fast enough, it would find that program, but usually it's just not. So in this case, we have 2 useful subprograms in each child of the conditional, and they're smaller, so we'll likely see them. The first satisfies 2 out of 6 examples, and the second satisfies 4 out of 6 examples. We can show these to a user who can then wrap up the solution all on their own. Our paper includes an exploratory user study where we let some people do just that. Check it out for the details. We evaluated our tool, Bester, on the Cygus competition benchmarks. But first, we had to get some errors into them. So we added at least one error to benchmarks from the Cygus suite. And we ran them with both Bester and CBC4, which is the winner in the Cygus competition's PBE strings category for years now. But actually, you can't just run CBC4 because it will try to find something to fit all examples. So we ran it both against the full specification and against each one of the specifications where one example is dropped, which is our original naive solution that we started out with. And we ran CBC4 in each of these modes twice. Once until it was done with all the subspecifications, and once with the same timeout as Bester. And actually, since we randomized the order in which CBC4 gets these new subspecifications, we also ran each of these 5 times. So first we looked at how high the result that we're expecting was ranked. This graph shows for how many benchmarks we would see the target program if we only looked at the top 1 result, 2 results, and so on up to 5. Bester covers almost all of the benchmarks with top 2 results and all of them at top 5. Neither version of CBC4 does nearly as well. The version that does best, though, is the one that has no timeout forced on it and gets to run through all of the subspecifications to completion. So let's see what happens there. If we look at termination, both Bester and the version of CBC4 with the timeout terminate by that timeout, 45 seconds, on all benchmarks. The version of CBC4 that gets to run freely still doesn't terminate on all benchmarks at 2 minutes. We do show in the paper that when there's no error in the specifications, CBC4 does better than Bester, but not by that much. And in the case where there are errors, Bester has a big advantage by only having to run once, which gets bigger the more errors are allowed in the spec. Here, CBC4 only allows for 1 error. So to sum up, I talked about what we can do when a specification has errors, and we still want to do the best we can. That we want to try every subset of the examples and see what works, and how fortunate it is that with observational equivalence, we can look at all the subsets of the examples at once. This can find multiple best effort results, so I also talked about how we rank them. I talked about how this relates to hard problems and how we evaluated this, although I didn't cover all of our experiments, so if you're interested, you should peek in the paper.
Hooray!